So in chapter 8, we're going to extend trigonometry a bit to non-right triangles and a few other things. So it turns out we can apply trigonometry to triangles that don't necessarily have a right angle. So let's make an obtuse angle up there. So this angle up here is bigger than 90, less than 90, less than 90. The three angles add up to 180 because it's a triangle. We can apply these sines and cosines, which are right angle functions, to non-right triangles by just considering that from any vertex, I can drop a perpendicular line, an altitude, and that altitude makes a right angle. And then I can break this into two right triangles. And then each side allows me to apply trig functions. Now, when we do that, some really cool consequences come out of that. So one is called the law of sines. So let's call this angle over here alpha, and I'm going to get rid of that altitude. Actually, I'll just delete it this way. Come here, altitude. And you can go away too. So let's call this angle over here alpha. Call this one beta, and this one gamma. And then the sides of the triangle we'll call side A, side B, B opposite beta, A opposite alpha, and C opposite gamma. And what the law of sines says is ratios of the sine and the lengths opposite always match. So that is the sine of alpha divided by A is going to be equal to the sine of beta divided by B, which is equal to the sine of gamma divided by C. Right, so these ratios, and we can look at them in either way. Here I have the sine over the length. You could flip them all and do it the other way. So an alternate version of this would be the length divided by the sine equals the length divided by the sine. The length divided by the sine. So there's a couple different ways we can look at that. And important things about this is it's always got to be the side opposite the angle, because remember, in a right triangle, remember the sine is opposite over hypotenuse. Okay, so it has to be the side opposite the angle. And so we're just going to look at some applications of that. Next part of this section 8.1, there's an extension of the Pythagorean theorem. Remember, the Pythagorean theorem only applies to right triangles, but it turns out with these trig functions, we can do a generalized version of the Pythagorean theorem that'll apply to any triangle, even non-right ones. We'll do that later. So next we'll look at an application of this. Let's pull one out of your homework. So again, the point of this is we're going to start playing around with triangles that aren't right. And we can do that if we know enough information about sides and angles. So let's give this one a shot. And one thing that I want to be careful about is I want to use my calculator wisely and only round at the end and not on intermediate steps. So use my calculators, all the decimals it records for any particular number. All right, so what do we got here? We need to figure out X, and we know that X is opposite that 14 degrees right there. 13, the length, is opposite the 16 degrees here. So if we apply the law of sines to this, starting with the x divided by the sine of its opposite angle, which would be the 14. And when I use my calculator, I got to pay attention that this is degrees, not radians. So that's going to have to be equal to, since I started with a length in the top, I have to do that length in the top, 13 over the sine of 16 degrees. And again, it's got to be the angle opposite the side. 16 is opposite 13. So to solve for x here, I just need to multiply the sine up to the other side. So x is going to be 13 times the sine of 14 degrees divided by the sine of 16 degrees. And there's really nothing much I can do besides plug into the calculator. And as far as rounding goes, I don't want to find the sine of 14 and then find the sine of 16. I can just type this all in one shot into my calculator. So don't do intermediate steps like that. Your calculator you can type these expressions straight into it. And we'll see if that seems reasonable here in the picture. Picture's not drawn to scale, by the way. You can tell that. Okay, so we've got, I forgot the numbers, 13. 13 times the sine of 14, and by default, Desmos is in radian mode, so we need to change to degree mode. And remember that later, divided by sine of 16 degrees, and double check the notes that I got those in the right spot. Yep. So my calculator says that missing length x should be about 11 point, how many decimals does it want? 4, it's a lot. 11.4099. Next, I want to ask if that's reasonable. So this is approximately 11.4099. And one thing that's going to be true about triangles is smaller angles are opposite smaller sides. Bigger angles are opposite bigger sides. Now, they're not directly proportional, the angle to the side. If they were, we could just take x over 14 equals 13 over 16, but that doesn't work. The sine has to come in there, turns out. So they're not directly proportional, but they're proportional related to the sine of the angle. So x should be smaller than 13 because 14 is smaller than 16 and they're opposite each other. And this is a little smaller than 13, so that seems reasonable.